So, two ways to increase the strength of a contraction is to activate more motor units or to increase the frequency on one motor unit. Now let's look at the different types of graded responses. So let's look at a graded response where you increase the frequency. If I hit the muscle before it completely relaxes after the absolute refractory period, when the muscle contracts, it's going to contract with more strength. Why is that? Because some of the calcium is still out, so you don't have to wait for the calcium to be, as much calcium to be released. So this is called wave summation. You're adding the waves together. Now there's two kinds of wave summation. There is wave summation where you just have an unfused, it's just a gradual, like going uphill after hill or steps. All of this is adding together, but it's not a solid sustained contraction. It's more of a quivering contraction. So this is unfused or incomplete. Sustained but quivering contraction due to high frequency of stimulation. Now, if you hit it with more frequency than we're seeing on this slide, then it will fuse together. So we're going to hit it so many times that you're just going to sustain, or you're going to hold the contraction. There's no quivering. It's smooth. This is called tetanus. Now when you think of tetanus, you may think of tetanus shots. The bacteria Clostridium tetani releases a toxin that will lock up your muscles, lockjaw. And so what you're doing here is you're locking up a muscle temporarily, and it's called tetanus. We don't want it to lock it up permanently. All relaxation disappears and you have a smooth sustained contraction. Prolonged tetanus can lead to muscle fatigue. You can't hold a weight up forever. After a while you're going to run out of ATP. You're going to have ion imbalances, and that's going to you're going to be unable to sustain the contraction, mostly because you can't produce ATP. Another way to do, let me go back and show you what I'm talking about. Another way to have a graded response is to have changes in the strength of the stimuli. And when you change the strength of the stimulus, then you're going to recruit more motor units. Multiple motor unit summation, or called recruitment, increasing the voltage to a muscle and calling in more and more muscle fibers to play. So if I hit a muscle or a muscle unit with a sub-threshold stimulus, that's one that's not able to make a contraction, we'll see no contraction. It won't stimulate the muscle. But when we hit it with a voltage impulse that's strong enough to have the muscle contract, we've reached threshold. Well, what happens if I hit that muscle with a super threshold stimulus or a maximal stimulus? It's going to recruit all the muscle units in the area, and so the muscle is going to contract with its greatest force. So we're calling more and more muscle units into contraction. Most of the time with a muscle group, what you're really going to do is you're going to excite some in one motor unit, and then while they relax you excite another motor unit, and while they relax another motor unit, so that you can sustain the contraction. Maybe not give it the most forceful, but to sustain it. In weak and precise contractions, relatively few motor units are stimulated, while forceful contractions, many motor units are activated. Although all motor units may be activated to produce a strong contraction, more commonly motor units are activated asynchronously in the body to prevent fatigue. So some of them are going to rest while others are contracting. So what we've been saying in this section is the force of the contraction is affected by the number of muscle fibers contracting, the size of the muscle. If it's a bigger muscle, it's going to have more muscle fiber units, the frequency of the stimulation, and one more phenomena that we haven't discussed called the length-tension ratio, or the stretch. We know that actin and myosin are overlapping in a resting muscle. Well, when that myosin head reaches up to get that actin, it has to be there, and if your muscle is stretched too much, there's nothing for the myosin head to grab onto, and so you don't have a contraction. Now if the overlapping is too much, then your contraction is going to be very small. So that overlapping has to be optimum. Here it's too much, and so only 75% of the shortening. Here it can barely reach, and so it's not going to contract, it's just going to be stretched. And here is the perfect relationship, the perfect stretch, or the length tension relationship, so you're going to contract with the most strength. That's why muscle builders and people that are athletes do stretching before exercises so they can get that length-tension relationship perfect. Now, you know that in your anatomical position that your bones are extended. Well, to keep your bones extended and to have to be able to stand up, to have posture, some of your muscles are going to be slightly contracted at all times, and that's called muscle tone. It doesn't provide for movement, but it keeps the muscles firm and healthy and ready to respond, and it stabilizes joints and maintains posture. So to keep your muscles strong, you need to regularly exercise. When you regularly exercise, it causes each individual muscle cell to get bigger. That's called hypertrophy, and it increases their strength. They become more efficient at getting ATP. They are resistant to fatigue. But if you don't use your muscles, actually you will lose 5% of your muscle strength per day, and that's called atrophy. So you know, if you're in the hospital and you're bedridden, physical therapy is going to come and exercise those muscles so that you don't lose so much of your strength. If you were to stay in the bed for 2 weeks and not do anything, you couldn't get up and move around after the 2 weeks because you'd be too tired. Now, if you injure a muscle, the best thing for it is rice. And I'm not talking about eating rice. I'm talking about rest, ice, compression, and elevation. And you're only going to want to do that for a couple of days because you don't want to start atrophying. So after a couple of days, then you're going to alternate the ice with warm, and you're going to start slowly becoming active again. So we keep talking about that muscles need ATP and calcium in order to contract. So let's see how a muscle gets ATP. Actually, in your muscles, you have stored up ATP that will give you 4 to 6 seconds worth of energy. It's constantly being regenerated, but it's there and it'll provide you very quick energy. What happens is that the ATP that's stored is broken down into ADP, energy, and phosphate, so that by some other process we can create ATP again. One of those processes of turning ADP into ATP is by using creatine phosphate in direct phosphorylation. Now, don't let that word phosphorylation upset you. All it means is giving ADP a phosphate. And so creatine phosphate is found in the muscle, and it has a high energy molecule in that phosphate. And so if it reacts with ADP, it will actually give the phosphate, high energy phosphate, to ADP and form ATP and creatine. Creatine is going to break down into another substance known as creatinine, which is one of your major nitrogenous waste that the kidney has to get rid of. There is an enzyme called creatine kinase that helps this reaction take place. This providing of the phosphate from creatine phosphate gives you 15 seconds worth of energy. That's including the 4 to 6 from the stored ATP. So that's really only about 9 to 11 seconds by itself. Another way we can get energy is anaerobic glycolysis. Now, don't get upset about a big word. Anaerobic, without air, glycolysis, breaking glucose. And what you're going to form is lactic acid. So we break glucose into 2 ATPs and 2 pyruvic acids. The pyruvic acids are going to turn into lactic acid. Now, lactic acid gets a bad rep sometimes because if there's too much of it in the muscle, it can lead to muscle soreness. But actually, your liver, your kidney, and your heart can use lactic acid in the Cori cycle to produce energy. What they do is they convert the lactic acid into glucose, and then we can break the glucose down. Now, glycolysis does not require oxygen, so that's a good point, but it only gives you about 5% the potential from ATP, or potential ATPs from glucose. When we look at the aerobic method, you're going to see you can get 36 to 38. So it's really better to break your glucose down using oxygen, but maybe you don't have enough oxygen available because you're running a marathon. So it occurs very fast, but it only produces 2 ATP. So this is a little picture from your book that shows glycolysis occurring in the cytosol of the cell, where we break glucose down into 2 ATP, goes into pyruvic acid and then lactic acid. So looking at the stored ATP, creatine phosphate, and glycolysis, you have 30 to 40 seconds worth of energy. But, like I said before, if you get lots of lactic acid, it can lead to muscle fatigue and soreness. So what's going to get you through a marathon? What is the ultimate way to get ATP in the muscle? That is aerobic respiration. That is using oxygen to break down glucose into ATP. This occurs in the mitochondria. Remember, it's called the powerhouse. And there's a series of reactions known as oxidative phosphorylation. Again, don't be upset. We're giving ATP a phosphate, so that's phosphorylation, and we're using oxygen. So glucose plus oxygen gives you carbon dioxide, water, and 36 to 38 ATPs. It involves glycolysis that we talked about, which is really anaerobic. Then that pyruvic acid will be pulled into the mitochondria. That's transition. Then it goes into the Krebs or citric acid cycle, and then the electron transport chain. And what you will net is those 36 to 38 ATP. Now, if you cannot provide enough ATP for your muscle, then it cannot contract anymore, and even though a stimulus might be being sent, and that's called muscle fatigue. One part of muscle fatigue is lactic acid being built up, and also ion imbalances can contribute to fatigue. Remember, the calcium goes into the neuron, then the acetylcholine goes across the cleft, then sodium goes in and potassium goes in. Calcium is released from the sarcoplasmic reticulum. You have a lot of ions moving across membranes, and so if they're not back to where they're supposed to be, this could cause fatigue as well. So if you experience fatigue, maybe because you're not getting enough oxygen, after exercise we have to pay back the oxygen debt. That's what we used to say. Now they're saying excessive post-exercise oxygen consumption. Think about after you've just run a race, what will you be doing? Right? Breathing very fast. So you need an extra amount of oxygen to restore the oxygen reserves in the myoglobin of the muscle. You need that extra oxygen to convert lactic acid to pyruvic acid or glycogen, which is how we store glucose, to restore the glycogen and also to resynthesize that stored ATP and the creatine phosphate. So after you've used all the energy available, you're going to have to pay back the oxygen debt, and in doing that you're going to set up all of your reserves of ATP again. Higher levels of lactic acid trigger the respiratory center of the brain and cause us to increase our breathing. Now, if you remember, one of the functions of muscles is thermogenesis. Even though the muscle is in a lever system, no lever system or no system of work is 100% efficient. So only about 40% of the energy in glucose is used to make the muscle contraction. The rest of it is heat, and they think of heat as an unuseful form of energy, but we know that it helps us maintain 37 degrees Celsius or 98.6 Fahrenheit so that all of our proteins and our enzymes can work right at our optimum temperature. So let's stop here, and then we'll talk about velocity and duration of contractions, talk about smooth muscle and cardiac muscle a little bit, and we'll be through with this chapter 9.